This video is on spectral factorization, something that is studied in digital and discrete signal processing courses. What I'll try to do is state and prove this theorem very rigorously, something that is not quite done well in the books. And the book that I'm using as reference is by Hayes, Digital Signal Processing and Modeling. The chapter that you should look for is chapter 3, section 5, page 104. Now, before going any further, I should mention that one should really have proper background knowledge on concepts like power spectrum, WSS processes, core-to-core relation sequences, etc. to fully grasp the concept of this theorem. So, what's the spectral factorization is about? We all know what a power spectrum is. A power spectrum for a WSS signal, YK, we can always find its power spectrum, Py, as a function of a complex variable.
Then the spectral factorization is all about the reverse process. That is,
let's say we are given a random function Py as a function of z. Then what properties should this Py have so that we can always find a WSS signal Yk so that its power spectrum will be Py? And as it turns out, with certain restrictions on Py, we can always find the signal Yk so that its power spectrum will be Py, and also we can produce that signal Yk with only a white noise as input inside causal stable filter Q. So what this theorem tells us is that analyzing purely the theoretical properties of Py, we can always answer the questions like, can there exist such WSS processes, and how to produce it? Can we produce it? These questions purely based on theoretical assumptions and theoretical analysis. For a little bit of background here, for a WSS white says stationary signal xk, its autocorrelation sequence is defined to be this, which is an expectation value. The autocorrelation sequence is basically a statistical property of a signal. Then its power spectrum is defined to be the Z transform of this autocorrelation sequence, where we have assumed that the mean of this signal is 0. Then this power spectrum has a definite property, which is that its value on the unit circle in the complex plane is non-negative, something that I have proved at the very end because its proof is not very pleasant. Now I'll try to find and state the relationship that exists between the power spectrums of input and output of a linear time invariant system. And as we know that power spectrums are directly related to the autocorrelation sequences, so if we can find the relationship between their autocorrelation sequences, then we can find the relationship between their power spectrums. So what's the situation here is that we have a linear time invariant filter H with a WSS of 0 in input X, then we'll have a WSS output Y. Now, how do you know that the output signal will be WSS? There are a few requirements out there for a signal to be WSS. Most of them are fulfilled by the fact that the input signal is WSS and the filter is a linear time invariant filter. And I'll suggest you to go through the book that I have referred above, page 100, for full disclosure on this topic. And I'm particularly interested in this one fact, which is that the filter will have to be stable. Why do we need the stability of this filter? One of the key decisive requirements of a WSS process of a signal to be WSS is that its variance will have to be finite, and as we will see, the stability of the filter ensures that the variance of the signal is finite. But before that, we need to find the relation between the two autocorrelation sequences with some trivial intermediate steps, something that is derived in the book, page 100, the referred book, and something that is I'm not going into the details because That's not the point of this video. So this is the final equation that we stumble upon. Rx is the autocorrelation sequence of the input signal and Ry is the autocorrelation sequence of the output signal. And both of them are related in a convoluted way with the filter signal, which we write like this in a compact form. This is basically a double summation over two indices L and M, with the mean of the signal is 0, of course. Now let's come to a point of interest, which is that why do we need a stable filter and what does stability even mean? So in the context of signal processing, we say that the filter is stable if the summation of its absolute values, signal point values, or all the range that's possible is finite, which in this case we denote by R. Then the filter is called stable. And now we'll see how this stability of the filter implies that the variance is finite for the output signal Y, which is basically a key requirement for the output signal Y to be a WSS white sands stationary process. Now one should know that the variance of a signal is closely related to its autocorrelation sequence at zeroth phase difference, and they are basically equal. And we also know that at zeroth phase difference of autocorrelation sequence is a positive number, hence its value and its absolute value will be equal. And this is the relation that we have proved above, where the autocorrelation sequence of the output signal is related to the input one. And now if we go through some equality and inequality relations. For example, in this line we have used the fact that the absolute value of a term is always greater than the normal ones. And in this line we have used the fact that autocorrelation sequence at zeroth phase is always greater than any other phase difference, is greater than any other autocorrelation sequence at other phase difference. And finally in this line what we did was take out this constant term out of the summation, and what remains is 2 summation multiplied with respect to two different indices L and M. So finally what remains is that the variance of the output signal is less than equal to the variance of the input signal multiplied by the term R square, something that we have defined and denoted by R above. Now we know that the input signal X is a WSS process, hence its variance will be finite. And also we have established the fact that the R square is finite above, hence this term is also finite, which thereby implies that our output signal will be a WSS process. Now finally, if we use this input-output relations of the autocorrelation sequences to find the input-output relations of the power spectrums, knowing the fact that the power spectrum is basically the Z transform of the autocorrelation sequence, and the fact that Z transforms over convolutions are basically Z transforms of each term multiplied together. So what it turns out is that the power spectrum of the output signal is power spectrum of the input signal multiplied by the power spectrum of the filter signal, and this complex conjugate like term of the filter signal. So these two are obvious, right? And this is the term that is easy to derive, which is basically the Z transform of this term, which is a complex conjugate of the input filter signal taking a negative index k. So this is the proof that I did, which I am not going into the details of. You can pause this video and verify that this is the case. So what we finally end up is this important relationship between power spectrums for a linear time invariant stable filter HZ. Now it's time for the actual core topic of this video, which is actually finding signals, input signals and the filter that are necessary to produce a filter having this power spectrum. Now sometimes, in fact most of the times, what will happen is we'll encounter functions py of z so that factoring this function of a complex variable z into these multiplied versions, we will be explicitly able to express this function as multiplication of three functions like this. Then it will be really obvious that this will be the input signal and this will be the filter signal. So we will see an example. So in this case, suppose we are given a function p of y as a function of complex variable z, and if we try to factor it into our required form factor, it turns out that we can, where this is our filter signal and this is the power spectrum of the input signal, and this is the term, a conjugate term, that is required to be in there. Now, how do we predict the input signal? The filter signal is already being predicted as we have its Z transform. So what we'll need to do is just find the inverse transform of it. So there can be many functions out there having a constant power spectrum, hopefully, but there's one type of signal that we can produce regularly and we can control its variance, which is white noise. So we can produce a white noise having a variance 4, and we know that for a white noise its variance is equal to its power spectrum. We can take that white noise as input inside this filter signal, which is inverse transform of qz, and this is a causal signal, so it maintains its property that's needed for y to be w as a process. So for this function, it turned out to be a straightforward process to find this factorization and find the input signal and the filter that is necessary to produce a signal a ws as y having a power spectrum py. But we will not necessarily always be that lucky with all kinds of functions. For example, for this given power spectrum of the output signal, there is no obvious way to actually factor these functions into this form. But as it turns out, using the spectral factorization theorem, we can readily say that this function can be factored into this form, where the input signal will be a WSS white noise and the output signal will be a causal stable filter. Sorry, the filter will be a causal stable filter. So this is the very general output case of this theorem, and we are going to prove this from this general point of view, where we'll be given a power spectrum and we'll predict what properties should this function have, so that we can always produce a signal y having a LTI stable filter q and an input signal which will generally be a white noise. So the condition that we impose on py is that when you take the logarithm of that function, it should be an analytic function, that is this logarithm of this given power spectrum. It should be analytic on a given particular analysis. So we will come to this term later. Basically, analyticity corresponds to the differentiability of that function at a particular area or region, and an analysis means the area that exists between two circles. One is smaller, another is larger. So the requirement is that this analysis should contain the unit circle. In this region, if this function is analytic or in other sense differentiable, then we can say then this pyz can be factored with the above defined properties. Now, one needs to be familiar with three key concepts. First one is analyticity, next one is power series expansion, and the third one is Laurent series expansion. If you want full exposure on these topics, I have referred some books in the description. You can check those out. But for now, what I'm going to do is state these concepts with as much clarity as possible, and then use these ideas to basically prove this theorem. Now, one way to explain analyticity of a function at a point z0 is that it will have a power series expansion around that point, but as I have not defined the power series expansion yet, I'll try to tackle this definition from a different point of view, which is basically an equivalent point of view giving the same result. So for a function f at a point z0, we say that it's analytic at that point if its derivative exists at that point. And what you mean by derivative is basically its differential value, and we are familiar with this limit in one dimensional case where we take the limit, that is, we try to reach the value z0 and divide that by its difference. But unlike one-dimensional case, we can reach this z0 from all directions possible, and there may be uncountable ways, uncountable different directions from which we can reach this point z0. And differentiability means that no matter from which direction we reach z0, this limit should exist, and not only should it exist, all its values should be same. Then and only then we can say that the function is differentiable at that point, hence analytic. But it's a gigantic job to actually check, kind of impossible, this limit, the value of this limit going to z0 from all different ways, from all different directions. But luckily we have Cauchy-Riemann equations for the rescue. It says that for a function f, if it's a function of a variable z, complex variable z, but not function of its complex conjugate z0, and the derivative of that function with respect to the z in our traditional sense, if this derivative exists, then f can be said to be analytic at the points where this derivative exists. And measure the function that we'll encounter will be like a function of a complex variable but not a function of its complex conjugate. Hence it will be really easy to do this differentiation and find the existence of this derivative, hence saying or ensuring that our function is analytic. Now, what's a power series? Power series is basically a function being expanded into an infinite series, and this series must converge where the exponent is taken over infinite values. And as it turns out, if we have a function which is analytic at a point z0, then we can expand that function around that point, around that z0 as a power series with coefficients vn, where the values of this coefficient are unique, fixed values. So analyticity basically ensures that we can expand the function into power series, and these values, these sets, are actually taken around this point. So c should be close to the point z0 for this series to converge, which means that the radius of convergence of this series is basically around this point z0. Now finally, if we talk about the Laurent series, this is also about expanding a function, but this time it's on an annular area. So suppose we have a function capital F which is analytic inside an annulus area, where the let's say the smaller radius is r1 and the bigger radius is r2, and the function f is analytic in this middle region. Then this function can be expanded as a series expansion with coefficients cn, and the z, the complex variable z, should be inside this annulus area, and the sum is taken from negative infinity to positive infinity. Now this expansion has some added decisive properties that will be very crucial in our analysis. If we separate this summation into three terms, first one is taking all the negative indices, second one is taking only the 0th index, and the third one is taking all the positive indices, and we denote the first summation as f2 and the last summation as f1, then these functions will have their very own important properties, such as the f1 that we have defined is actually analytic outside the smaller ball, a smaller radius that of the above defined annulus. So in the whole region expanding towards infinity, this function is analytic. It is differentiable. And the second function f2, which is this expressed, is actually analytic inside the R2 ball, that is inside the bigger radius ball. So in this whole region, this function is analytic. Now this analyticity of this function will come very handy later, so you should remember it. Now we come to the main part. As we have mentioned already, that the logarithm of the given power spectrum is analytic inside an annulus area containing the unit circle in the complex plane. We can Laurent expand that function for all the values, all the z's inside that annulus area, something that we have just learned. So this is the desired Laurent expanded expression of this function. Now in this expansion, if we take the values of the z on the unit circle, we find that this new expression, this new infinite series, is basically the Fourier series expansion of this function. Hence, these ck are the Fourier coefficients. So you can find the values of the coefficients inverse, taking inverse Fourier series, which is this integral. Now, one more property that I have forgot to mention, or one more required property about the power spectrum, given power spectrum function, is that its value on the unit circle should always be real and positive. For a WSS process, the power spectrum of that process should be always positive on the unit circle, something that I'll try to prove later down the video. So as we are expecting that the given power spectrum is of a WSS process, so naturally it should be the case that its power spectrum is positive on the unit circle. So on top of the requirement that the function should be, the logarithm of the function should be analytic inside the annulus, this should be another required condition that the power spectrum, the values of that function on the unit circle should be positive. Hence the logarithm of that function should be defined and also be positive. So in that case, if we take a complex conjugate on both sides, what we see is that the complex conjugate is equal to ck with negative index. Also, the zeroth complex conjugate is integral over all positive term, hence this term will also be a positive term. Now if we take exponential over this term, and also knowing the fact that if we take the exponential over the logarithm of a term, then the output will be the term itself. And on the right hand side, if we use this term and express the logarithm as a Laurent series expanded version, and in that second line, if we divide this series expansion, if we divide this series expansion into three terms, something that we have shown when I tried to explain Laurent series expansion, f1, f2, and a constant term, a constant positive term, and finally we end up getting the multiplication of three terms. I denote this by q and denote this by rz and this by sigma square, the multiplication of all three of them being equal to py. Now if we further analyze the function rz, the expression, this is the expression of rz. Now if we do merely a change of variable, that is take a negative index, rather than the positive index, we get this expression. Now in this expression, as we have proved above, that the negative index of ck is the complex conjugate of the positive index, and here we just did merely a rearrangement of terms. So what we finally end up getting is conjugate over this summation. Now this summation exponential term is same as the qz function. So what we finally end up getting is rz is equal to the complex conjugate of the q, taking this as variable. So what we finally end up is this expression. Now at first glance it might look like our work is done. We can take inverse z transform of this function and find a filter that is causal and stable, and this is something that can be realized with the white noise. But our work is only half done. We have got a constant term which can be realized with the white noise, but we still don't know anything about this function qz. How do you know that this function is the z transform of a causal filter which is stable as well? So something that we need to prove. Now one should know that what causality and stability of a filter is. Causality basically means for a filter signal all its negative indices should be 0, and for a filter to be stable in the z transform in the z space, all the poles of that qz function should be inside the unit circle. Poles are basically the points at which the function qz is undefined or its value is infinite. So these points should be inside the unit circle, then and only then it will be stable. You can check the Broca's discrete signal processing book for more to find more about this. As we have seen above, that qz is equal to the exponential taken over the f1 function, where the f1 is this infinite summation taken from the Lorentz expansion. And as you remember that I have said in the when I tried to explain the Lorentz expansion, that this f1 summation is analytic outside the smaller circle, which in this case we denote by r. And according to our requirement, we know that this analysis should contain the unit circle. So the smaller circle should be smaller than 1, right? And as f1 is analytic in this whole region, qz should also be analytic in the whole region. It's a very straightforward verification, because if a function is analytic, then its exponential is also analytic or differentiable. So that means that in this whole region stretching from r to infinity, qz is all defined, well defined, so it doesn't have any poles in those regions, because poles are the points where a function is undefined. So if there are poles of qz, then all of them should be inside this smaller circle. Now as this smaller circle is inside the unit circle, so we can say that all the poles of the qz is basically inside the unit circle. But if the poles are inside the unit circle, then the filter is actually stable according to our requirement above. So we have proved that the filter is stable. Now, as we have shown above that q is equal to the exponential of the f1 function, then if we take log on both sides, what we get is this equality. And as we know that f1 is analytic, fully analytic, hence fully defined outside the unit circle, outside the circle of radius r, which is inside the unit circle of course, then due to their equality, the logarithm of qz should also be fully defined outside the r ball or circle of radius r. which means that qz can't have any zero, that is for any value z outside this circle. Qz can't be 0, because if qz is 0, then the logarithm is undefined. So if qz has any 0, it should be inside this circle of radius r, which is consequently inside the unit circle. So what it turns out is that qz has both poles and zeros inside the unit circle, and these kinds of filters are actually called minimum phase filters, which has both poles and zeros inside the unit circle. So the perk of a minimum phase filter is that it has a very stable inverse filter, because the zeros of qz becomes the poles of this inverse function, inverse filter. So this inverse filter is also stable, so we can use this inverse filter to get the input signal from the output signal, taking output signal as input inside this inverse filter. Now we'll try to tackle the causality problem of the filter. We will use this f2 function. All of them resides in the Laurent series expansion of the logarithm. As it's shown above, that the rz is the exponential taken over the f2 function, and rz is equal to this term. So this is the equality that we're going to use. And one should remember that f2 has the property that it is analytic inside the bigger ball, which in this case is a ball containing the unit circle of the analysis. So in this whole region, this function is analytic, hence its exponential will also be analytic. So what it basically says that this term is analytic inside this whole region, and what we'll try to do is do some power series expansion of this function and convert that power series expansion into a z transform, and thereby we will get a sequence of function, the z transform of which will be the qz, and as we'll see, this sequence will be a causal sequence. Now remember from power series expansion that for a function to have a power series expansion around a point, let's say z0, the function itself, which in this case this function, needs to be analytic at that point. So if we want to power series expand this function around z0, it has to be analytic at that point, something that we have ensured above. So as qz is analytic inside this whole region, including the center, so we can power expand that function around z0 equal to 0. So this is the expression of the power series expansion. Vk is the power series coefficient, and putting the value of the z0 to be 0, this is the term we get, and vk is unique, which means that there can't be any other series expansion of that function having a different value of vk. And this series has a radius of convergence inside the bigger circle, of course. So now what we'll do is do some clever change of variables. We take this change of variables to be p, and putting this value p, and our radius of convergence changes, of course, which in this case becomes the whole region outside outside the smaller circle, because p being the inverse of z, so the radius of convergence with respect to p will be the complementary space of the first one. So putting the change of variable inside and doing some manipulations, trivial manipulations, and taking the conjugate over this term, and redefining the term a conjugate of vk to be equal to qk, what we finally get is this expression,
which is very familiar, which is the Z transform of a signal, where in the last line we have again did a change of variable, just rename the p to be a complex function z, because both of them lives in the complex space, right? So this is the Z transform, and what we see that the negative index of this function is non-existent. So what it basically implies is that um, the inverse Z transform of this qz is a causal signal because it has no negative exponent, and the ROC of it, the radius of convergence of it, is the whole area outside the circle, smaller circle, and the value of the signal values is equal to the vk conjugate, which is unique because we know that vk is unique, hence its conjugate will be unique. So we have a unique Z transform of qz, hence qz is a causal filter. So what we can say that if we are given a power spectral function, a random function, so that its logarithm is analytic inside an analysis containing the unit circle, and the value of this function on the unit circle is positive, then we can always find a LTI stable causal filter QK, so that with a white noise with variance C0 as input, we can always find a WSS process as output, so that the power spectrum of this output will be the function Py. And in addition to that, as the filter is minimum phase filter, its inverse function will also be a stable filter. So if we take the output as input inside this filter, we can get the input function, input white noise, with the same variance as output. Now it's time to briefly talk about why the power spectrum of a WSS signal is positive on the unit circle. The argument for that is already there in the book, page 103 HS, but the argument is incomplete, so I'm not going to go through the details. I'll share this notebook on the description box, so whoever's interested can go over that notebook and see the whole arguments. Now what I'm gonna do is mention the contradictions that exist between the proof of the book and the original argument, the real argument. So in the book, up to this point, it's proved that the integral having the power spectrum as integrand over any interval, no matter how small, no matter how minuscule the interval is, this whole integration value is always positive. So from this they concluded that this power spectrum value should always be positive, otherwise the integral can't be that the integral is always positive on any interval if this is negative. But this argument is flawed. If you have a little bit of idea about some measured theory, you should know that there can be functions out there like this which can do some irregular jumps into the negative side, and still its integral will be positive. So if majority of the time the value of the term is positive, then the integral will be positive. But there can be countable number of times that this function will can take negative terms, negative values. So we need additional conditions to be imposed on the power spectrum, so that the positivity of this integral would imply that the power spectrum would always be positive. And one such condition is the continuity of the power spectrum. To prove that, I had to use some theorems. One theorem exactly from measure theory books. Whoever has the background can go through this. So it basically implies that if the power spectrum is continuous, then it has to be true that the power spectrum is positive throughout the whole region.